Okay, we're going to look at acid and base titrations today. So the titration is the setup where you have your burette, your conical flask, and you use your pipette and the retort stand all together. And what happens is that in an acid and base titration, we'd have the acid up in the burette, and then we'd have a certain amount of base, usually about 25 centimeters cubed, in the conical flask. What we would do then is we would drop the acid slowly into the base until a colour change happens. That colour change indicates that all of the reactants have reacted together in a certain ratio. So this is what the titration is used for. It's used to find the concentration of a solution using another solution of known concentration. So, for example, if our base solution in the conical flask, we didn't know the concentration of that, we could use the acid to find that out, because let's say we made up the acid, we know the concentration of that acid. So based on how much acid it takes to neutralize the 25 centimeters cubed of the base, we can work out the base's concentration. So let's just take an example of making up a solution first of all, because once we do these titrations, we first of all have to make up the solutions. So let's take a look at an example. Here's our little example there. So what volume of 10 molar HCl, that's acid, would be required to make 500 centimeters cubed of 0.25 molar solution? So we're going from a high concentration, so you might have this back in the laboratory, in the back room, and you don't want to have it to be at 10 molar because that's quite strong. You actually want it to be very dilute and be a 0.25 molar solution. And you want approximately 500 centimeters cubed of it. So what we're going to have to do is we're going to have to take what we have, which is the 10 molar solution, dilute it down using water until we get a concentration of 0.25 molar. So it's like when you're taking my waddy or squash, you don't want to take the strong substance and use that straight away. You want to dilute it down. So that's what we're doing. So to do that, we're going to use this formula, C1V1 equals C2V2. The C's stand for concentration and the V's stand for volume. And you see that the ones, so the one basically stands for the initial, let's say the initial volume, initial concentration of what you have. And then the C2V2 is what you want it to be. Okay, so I'm just going to, in yellow, this is the V2, that's the volume that I want to end up with. This is the concentration I want to end up with. And then up here is the concentration I have originally. So the only thing that's missing is V1 in this scenario. And I need to figure out what volume of this 10 molar solution do I need to take out to dilute it up to 500 centimeters cubed and get that new concentration. So all you have to do is fill it in. C1 is the 10 molar. I don't know how much of that 10 molar I need to take out of the bottle to make up the new solution, but the new solution, I want it to be 0.25 molar and I want to have 500 centimeters cubed of it. Okay, so that's going to end up with 10 V1 and that is going to be 125 centimeters cubed over here. Take that 10 across the line and you'll end up with the volume to be 12.5 centimeters cubed. So what does that mean? That means you need to take 12.5 centimeters cubed of the 10 molar solution and then fill it up in the volumetric flask until 500 centimeters cubed. When you do that, you'll achieve this concentration. Okay, I'm going to write up another one, and then you can give this one a go yourselves. Okay, there's your question. What volume of 18 molar, 18, H2SO4 would be required to prepare 10 litres of 1 molar H2SO4? Now when I do it, I'm going to just change that 10 litres into centimetres cubed, which is 10,000 centimetres cubed. Okay, remember 1 litre is 1,000 centimetres cubed. Okay, so you can pause and you can work away. Alright, so we're going to go in with our formula again. Our concentration originally is 18 molars. That's our original undiluted concentration. We want to prepare 10 litres of a 1 molar solution. And I don't know how much of that 18 molar I need to make up this new solution. So my original concentration is 18. I don't know how much of it I need. I want my new concentration to be 1 molar. And I want 10 litres of it, or 10,000 centimetres cubed. Okay, so bringing that 18 across, the amount I need out of that 18 molar is 555.56 centimetres cubed, so about half a litre. So I need to measure out half a litre of the 18 molar, and then, sorry, not half exactly, 555.56 centimetres cubed of that 18 molar, and dilute it up to the 10 litres, and that will give me a new concentration of 1 molar. Okay, so that's all about kind of in the back of the lab, prepping your acid for the concentrations and for the titrations that you're going to do. Now I'm going to skip on and I'm going to do a leaving cert question from 2020, I believe. It's higher level, question 1, and it deals with sodium carbonate solution, or your washing soda crystals. So I'm just going to put that up on the screen now. So here it is. So if you want to take a moment to read that and pause. Okay. So on the side, I'm just going to take out the important sections of this. So we have the washing soda, and it was measured out to be 3.46 grams. And it was made up into 250 centimeters cubed. Okay. And then the average titer is 21.5. And we do have the concentration of the HCl as well. Okay, and then the volume of base is 25 centimeters cubed. And then we also have the chemical reaction there as well. I don't need to write that out. Okay. So in this scenario, we have the sodium carbonate, the washing soda crystals are in our conical flask. We're titrating it against our HCl, which we know the concentration of. So we can work out the concentration and answer all of these questions down here, hopefully, based on the information we have. So let's look at question 1. The average number of moles of HCl used up in a titration. Okay, so what information do I have about the HCl section? So I know the average titer versus average is 21.5 centimeters cubed, and its molarity is 0.12 moles. And we do have a formula that is the number of moles equals volume times molarity over 1,000. Okay, so I do have the volume, I do have the molarity, so I can actually work out and just sub in all of those pieces of information into this formula. You'll need to know that formula off by heart as well. Okay, putting that into your calculator then, you'll work out that the number of moles after each titration is 0.00258 moles of the HCl in each titer. That's on average because we're using the average titer there. So that's our first one done. Now let's look at the number of moles of sodium carbonate neutralized in each titration. So if I look up at the equation here, I'm after working out on average how many moles of the HCl was used with each titration. If I know the number of moles here, I can work out the number of moles across the equation because we have the ratios. Now the second question is asking me about the sodium carbonate. Now if I compare the HCl to the sodium carbonate, it says I have 2 moles of HCl reacting with 1 mole of the sodium carbonate. That is a 2-to-1 ratio. Now if I have 0.00258 moles of the HCl, I can work out the moles of the sodium carbonate also. So how I do that is I can see it goes from 2 to 1, so I have to half the number because half of 2 is 1, okay? So I'm going to just half that number. And I'll get 0.00129 moles of sodium carbonate. Okay, so I can write that in as well. 0.00129 moles of that sodium carbonate. Okay, the next one, part 3. The number of moles of sodium carbonate in the 250 centimeters cubed solution. So when I worked out the number of moles of sodium carbonate neutralized in each titration in part 2, we got this number up here. And that is in the 25 centimeter cubed section, because that's in the conical flask. So how many moles would be in 250 centimeters cubed? All you have to do is multiply that by 10, because 25 goes into 250 10 times. So if I know that 0.00129 moles of sodium carbonate is in 25 centimeters cubed, well, I can just multiply it by 10 to see how much would be in 250 centimeters cubed. And that's that next one done. So not too bad. Okay, let's look at the next one. The mass of water of crystallization. The mass of sodium carbonate in 250 centimeters cubed of the washing soda solution. So mass. Now we always know we have this formula. Number of moles equals mass over relative molecular mass. So let's see, do I have the number of moles in the 250? Yes, I do. It's over here. Can I work out the relative molecular mass? I can always work that out because it's a periodic table. So let's fill this in. We've got 0.0129 moles of the sodium carbonate. I don't know its mass. The relative molecular mass then, I can do it over in the corner here. 2 sodiums, 1 carbon, and 3 oxygens. Add those all up and we should get 106. So I have the relative molecular mass there now. So I can fill that in. Now if I take 0.0129 and multiply it by the 106, I'll get the mass of the sodium carbonate in the 250 centimeters cubed portion. And that we can work it out to be like so. Okay, so you can see that there's a difference of the sodium carbonate in the 250 centimeters cubed versus what was actually weighed out. And that's because it's not just the sodium carbonate that's been weighed out, but there are also molecules of water attached to the sodium carbonate crystals. So we're going to have to work out how many molecules of water are attached to each molecule of the sodium carbonate. And that brings us on to the next question. So if we weighed out 3.64 grams of this substance here with the water molecules, and yet the sodium carbonate only comes to that amount, we can work out how much of the water is involved in the weighing process by subtracting them. So once you subtract them, you're going to get this number, 2.0926 grams of H2O, the water. Okay, because we're taking literally the amount of sodium carbonate away from the amount that was actually weighed out. So the surplus has to be the water part. Now, if we have the mass of water, I can work out the number of moles. So this section was asking for the mass. Now we can work out the number of moles of the water as well. So let's go back to this formula. Okay, so the number of moles, we have our mass on top. Relative molecular mass, well, H2O, so we have 2 ones from the hydrogens, the 2 hydrogens, and then 16. Work that all out in the calculator and we'll get the number of moles to be 0.116 moles of H2O in the 250 centimeters cubed portion. Okay, the last one. The ratio of moles of water of crystallization to moles of sodium carbonate. So it's telling you exactly what to do. We have the moles of water. We worked out the moles of the sodium carbonate. Let's write it up here again. So we need to put it as a ratio. It's telling you what to do. So the 0.0129 moles to the 0.116 moles of water to work that out. Okay, so to get this ratio in the simplest form, you divide by the smallest number. So divide each side by the smallest number, and you're going to get 1:9. So the smallest number there is the 0.0129. So you're going to divide each side by that number and you'll get 1:9. So that means that this little x value up here is actually for each molecule of sodium carbonate. We are now not going to have the x, we're going to have a 9 molecules of water are also attached. And that is that question, that exam question completed. This was the calculation side of it. There are procedure questions that go along with it in regards to how to make up the solution. But you should be well able to do those ones. Okay, so that's the end of that one.